Hello students, welcome back to the another video lecture of ADA subject. In previous video lecture, we have discussed about our asymptotic notation, means what are this asymptotic notation and why we use asymptotic notations that were of three types. First one was big O notation, second is omega notation, and third one is theta notation. In previous lecture, we have discussed about big O notation. In this video lecture, we are going to learn about our second notation, which is our omega notation. So let's start with omega notation. So the omega notation represents lower bound in algorithm running time. So previously we have seen that big O notation was the upper bound for the algorithm's running time, and here omega is the lower bound for algorithm's running time. It represents the best case of algorithm time complexity. Example, minimum time required by an algorithm to complete. Previously, we have seen that for a linear search algorithm, if our elements found on the first position, then that was the best case of our algorithm. So here our omega notation represent the best case of algorithm time complexity. Let's see its definition. Its definition says that function of n is equal to omega of g of n if there exists a value of positive integer and an n0 and positive constant c such that function of n greater than or equal to c into g of n for all n is greater than or equal to n0. Hence, function g of n is a lower bound for function f of n. So, as the big O notation here, our only change in condition is that our function should be greater than or equal to c into g of n, where in our big O there was a condition that our function should be less than or equal to c into g of n. So for that, let's take an example. Example is 3n plus 2. So for 3n plus 2, our right hand side of equation must be less than or equal to our fn. So keep in mind that this condition function is greater than or equal to c into g of n. So for this we have added 1n. So in 1n, 1 is our c and n is our g of n. So for that, let's check with n is equal to 1. So here 2 plus 3 greater than or equal to 1. So that is true. Why? Because 5 greater than or equal to 1, condition true. For another example, let's take n is equal to 2. So 2 into 2, 4 plus 3 greater than or equal to 2, means 7 is greater than or equal to 2. That is true. So we can say that for all n greater than or equal to 1, this statement will be true. So for that, we can say this is our fn, 1 is our c, and n is our g of n. So from that equation, means from this our definition, we can say function is omega of g of n. So here our g of n is n. So we can write function of n is equal to omega of n. Again, understood why we write omega n, because our g of n is n. So we can write function n is equal to omega of n, means omega of g of n. Our g of n is n, so function is equal to omega of n. Okay. So here we have this series which is suggests lowest to the greatest numbers. So in that our function is 3n plus 2. So that belongs to the n. As we seen in our example, fn is equal to omega of n. So this belongs to the n term. This is our upper bound and this is our lower bound. So n will be our average bound. So for other examples we can check for the other polynomials also, and we can found our omega notation for different polynomials. So this is it for this omega notation, means omega notation is suggest lower bounds or suggest best case possibility of your algorithm's running time. Okay, so this is it for omega notation. Thank you, students.